All right, let's take a look at problem 13. So we're told that we have oxygen in a closed system that's compressed adiabatically from 25 degrees C in 1 bar to final temperature 450 degrees C. Then it is cooled under constant pressure until the temperature falls to 5 degrees C. Assuming oxygen to be an ideal gas, A. Draw a quantitative PV graph and show the process. B. Calculate the final pressure. And then calculate delta U, delta H, Q, and W for the entire process. And then we're asked if it's correct to assume that oxygen is an ideal gas under the conditions of the problem. And we're given a value of the heat capacity, and we're not given a temperature dependence, so we'll assume that it's constant. All right, so there's a lot going in there. And so what I'll start by doing is I'll start by drawing out our process, since it looks like there's 2 steps involved. And then I'll just solve the problem in its entirety. And then once we have, say our PV information throughout, along with, we'll calculate delta U, delta H, Q, and W for the entire process. Then we'll go back and talk about what that would look like on a PV phase diagram. So all right, so I'm going to draw a picture. So we're going to start with some initial state 1. And in state 1, my temperature is 25 degrees C, and my pressure is 1 bar, and it is going to be adiabatically compressed. So we have adiabatic, which tells us that Q is equal to 0, compression. Okay, so this is going to be a case where Q is equal to 0, but it's being compressed, so presumably my volume's decreasing, so we can't use one of our tricks of, say, assuming that volume is constant. So in state 2, so it's being adiabatically compressed to temperature T2 of 450 degrees C. Let me make that look a little better, 450 degrees C. And then from there, our system at 450 degrees C. Okay, so then next it's being cooled under constant pressure. Okay, it's being cooled under constant pressure to some system at a final temperature of 5 degrees C. Okay, where I'll just make a note that P3 is equal to P2. All right, and we're told we have an ideal gas. So let's go calculate everything we could possibly want to calculate for this process. All right, so let's start with state 1. If I wanted V, because we said we're asked to sketch our process on a PV phase diagram. Since I know T and P, since I know 2 independent intensive properties, the state of my system's fixed. So if I want to calculate V, I could do so using my ideal gas equation state. All right, so PV equals RT, so V1 would be equal to RT1 over P1. So since I know P1 and T1, I could go ahead and calculate V1. Just need to be careful about units, making sure I'm using absolute units for temperature, and then I'd probably convert pressure to Pascal just to make sure everything works out in SI units. Right, and we can calculate that once we get everything set up in MATLAB. Right, but let's kind of just work through the problem in general. All right, so for this first step, from 1 to 2, we're told we have adiabatic compression. Right, so Q is equal to 0. So what that does for us is in our first law energy balance, right, I have delta U, du, is equal to Q plus W, where Q is equal to 0. So my first law of balance reduces to delta U is equal to W. All right, so what I'm going to assume is that the only work exchange between my system and surroundings is reversible PV boundary work. Okay, and what I'm going to additionally do, okay, is I'm going to write this in its differential form, just so we can obtain our simplified expression for adiabatic expansion or compression that's given in the book. So instead of delta U, I'm going to write it as du is equal to, and I'm going to write del q, right? So to remind myself that, w in theory is a path function, although I could write d here since it's reversible boundary work. Okay, and so as I go from there, so du, okay, will be equal to cv dt. Okay, and here I have an ideal gas, and my reversible boundary work is going to be negative p dv. Okay. All right, and actually we'll write that as v of an ideal gas. Okay, and so then if I want to get delta u, all right, and I wanted to get my work, I would need to integrate the left and right hand side. What I'm going to do though first is I'm going to use my ideal gas equation of state. Right? If I wanted to integrate this equation, I would need to know how P changes with respect to V. Now it's a little challenging here because for my ideal gas equation of state, I can get P is equal to RT over V. But T is not constant, right? So T is changing as is V, right? So you just can't integrate that expression. And so we'll need to tweak things a little bit. All right, so what we'll do is ideal gas equation of state, we'll get that P, so we know PV is equal to RT. So P then is equal to RT over V. Okay, and I'm going to put a superscript on here to remind myself that this is an ideal gas. We're using the ideal gas equation of state. So CV dt then I could write as negative RT over V ideal gas times dV ideal gas. All right, so I'm going to bring T now over to the left-hand side, and I'm going to write this as CV over T dt is equal to negative R over VIG dV IG. All right, and maybe I bring R over, then CV is dimensionless. So actually, let me do that just because it'll make things dimensionless, which will be nice. So I can make -1, and I'm just going to bring R over here because CV and R will have the same units. All right, so then what I'm going to do is I'm going to take this equation, okay, now that I've brought my temperature dependence over to the left-hand side. In this, I'm going to integrate from my initial state, so T1, to my final state at T2. And the right-hand side, I'll integrate from, so now this will be V1 to V2. Okay, and so if we do that, okay, so we're told that CP is constant. Okay, so we're given a value of CP. Okay, but remember for an ideal gas, CP ideal gas is just CV ideal gas plus R. So if we know CP, we know CV, and CV is also constant. So R is constant, CV is constant, so I'm going to bring that out of the integral. So I'm going to write this as CV ideal gas over R, integral from T1 to T2, and that's 1 over T dt is equal to negative integral from V1 ideal gas to V2, okay, ideal gas, 1 over V ideal gas dV ideal gas. Okay, so let me add a new page. So working out the integral, so this is CV ideal gas over R. Then the integral of 1 over T is log. So this becomes log, and I'll have T2 over T1. Okay. No need for absolute values or anything. All right, we'll, it's assumed here we're working with, absolute temperatures. Okay, so I'll have CVIG R log T2 over T1, and I should emphasize here. So before, when we had CV delta T, we said, well, it doesn't matter if I'm in degrees Celsius or if I'm in Kelvin, because I have a difference in temperatures, right? And so difference in degrees C is the same as different in Kelvin. Okay, but here I have a ratio of T's, right? So it's imperative that you use absolute values. Okay, and that's going to be equal to So again, I'm going to have my log term. Right, so no need for absolute value sign because I know those are going to be positive. Then this will be negative log. Okay, and I'll have v2 ig over v1 ig. Okay. All right, so the next thing I'm going to do is volume's great, but I'm going to convert that so that I have pressure in there instead. And so how I can get rid of that, and I could keep volume if I wanted. Actually, let's work out the expression multiple ways, okay? Because it's all the same. Okay, the first thing I'm going to do is I have log T2 over T1, and then that's times CVIG over R, so I could bring that up. So I could write this as log T2 over T1, okay, raised to the CVIG over R is equal to, and then I'm going to use the negative sign and I'm going to flip it, log V1IG over V2IG. And then I'll take the exponential of both sides, and I get T2 over T1 raised to the CVIG over R is equal to V1IG over V2, okay, IG. Okay. And I could work with volumes, okay, or I could convert to pressures if I wanted to. Okay, the key there would be that V1 would be equal to RT1 over P1, and V2 would be equal to RT2 over P2. Okay, so if I were to plug that in, I get T2 over T1. So let me box this one in because this is a valid equation. Okay, but if I were to convert, I get T2 over T1 CV over R is equal to, so R would cancel, and I'll get T1 over P1 divided by T2 over P2. Okay. So that'll be equivalent to, I'm going to write this as T1 over P1, T1 over T2. So I have, write this as T1 over T2, and then times P2 over P1. Alright, so then if I multiply both sides by T2 over T1, so now I have T2 over T1 times T2 over T1 to the CVIG over R. Okay, well, this is equivalent to, so if I had, x times x, right, it's equal to, x squared, right, x 1 plus 1. So here, right, this is T2 over T1 raised to the CVIG over R plus 1, and that's equal to P2 over P1. So if I want to work in terms of pressure, I get T2 over T1 raised to the CVIG over R plus 1, and that's equal to P2 over P1. Phew. Alright, so if I needed P2 then, okay, and I know T2 and T1, okay, I can get that P2 is equal to P1 times T2 over T1 raised to the CV over R plus 1. Okay, so I can go ahead and I can calculate P2, and then once I have P2, I could get V2 is RT2 over P2. Okay, so using that for this state here, right, I'm able to get P2, so I can get V1 for this state, I can get P2, and I can get V2 here. Okay, Cool. So that's characterized, and then since I know P2, when I get to my third state here, right, I could go ahead and I could calculate V3, because V3 is just going to be R T3 over P3, where I know T3 and I know P3, right? Cool, so I can get all of my temperature, pressures, and volumes for all those states. No problem. All right, so now the next thing that we'll do, and actually let me go ahead and I'll calculate all those pressures and volumes before we forget. And then I'll go back and I'm going to calculate delta U and delta H. So the key with calculating delta U and delta H is, remember, for an ideal gas, U and H are only a function of temperature. Okay? So delta U is just going to be a CP delta, delta U is going to be a CV delta T, and delta H is going to be a CP delta T. Okay, and so we can get that. They're state functions, so I can just do my final state 3 minus my initial state 1. And then Q and W, those are going to be path dependent, but I can calculate Q and W for each step, and then add them, right? No problem. We've got this. All right, so let me go over to MATLAB, okay, and I'll start a new script. And I'll do computing P's and V's. Okay, and so we'll have T1. So T1 is 25, and that's in C. And actually, let me just type it in, 25 plus 273.15. Right, so we'll just convert to Kelvin. So P1, okay, so it's 1 bar. And so what I'm going to do is I'm just going to multiply by 1e to the 5, so I know it's in pascals. So T2 was 450, okay, again plus 273.15, so I get that in Kelvin. Pressure I don't know. T3 is 5 degrees, and I'll add my 273.15 Kelvin to that, so I get that in Kelvin, and I don't know P there either. I'll need my gas constant. So R, that's 8.314, and that's in SI units, so joules per mole Kelvin. CV, so CV is given the problem statement, 29.4. Okay, and that is also in joules per mole Kelvin. And I'm going to go ahead and I'm going to compute CP. CP is going to be CV plus R, just in case we need it later on. All right, so let's go ahead and we can calculate V1. So V1, and so V1 will be in units of meters cubed per mole, since I'm using SI units. So V1 will be equal to R times T1 divided by P1. Okay, then going to state 2, we can start by calculating P2. We have P2. So P2 is going to equal to P1 times, and then I have T2, and again I converted everything to Kelvin, divided by T1 raised to the, I have CV divided by R plus 1. And then once I have P2, I can get V2 is equal to R times T2 divided by P2. Okay, where again I've already converted my temperatures all to Kelvin. And then as far as system 3 is concerned, okay, it'll just be P3 is equal to P2, so that V3 is equal to R times T3 divided by P3. so if I run that, okay, I get some pressures that are, well, let's see, my pressures are big, but my pressures are in Pascal, so I would divide by 1 e to the 5 to get that in bar. And I have volumes which look small, and those are volumes in meters cubed per mole. Alright, so I'm able to calculate all my pressures and volumes. And again, I'll just leave them in my MATLAB file where everything is nicely computed. The pressures are larger, but again, I would divide by 1 e to the 5 to get in bars. Okay, so next let's compute delta U and delta H. Alright, so the key for U and H is U and H are both state functions. And so I could calculate delta U for this step, I could calculate delta U for this step and add them together, but it's the same as if I had just done it for this step. Okay. And remember, for an ideal gas, delta U is just good for an ideal gas, and here we're told, so for an ideal gas, U and H are only a function of T, and here we're told that our heat capacity is assumed constant. So delta U is nothing more than CV delta T. Right, so you could quickly work out that if I did CV delta T for the entire process, it's the same as if I did it for the two intermediate steps and added them together. Okay, so looking, I guess you'd call it C. All right, delta U, okay, would be nothing more than CV delta T, which would be T3 minus T1, and delta H would be Cp times T3 minus T1, where Cv is going to be equal to Cp minus R. Okay, so if I come back up here and I want to calculate, so these will be in units of joules per mole based on how we have them. So we would have that delta U would be equal to Cv times T3 minus T1, and delta H would be equal to Cp times T3 minus T1. Alright, so I can calculate delta U and delta H, and those are in units of joules per mole. Okay, Q and W are a little different, right? And the reason is Q and W are path functions. Okay, so if I want to calculate Q, what I need to do is calculate Q for step 1 and then step 2 and add them together. And if I want to calculate W, I need to calculate W for step 1 and then step 2 and add them together. Okay, so let's start with Q. Okay, so Q will be equal to Q from 1 to 2 plus Q from 2 to 3. Okay. Well, Q from 1 to 2 is just 0 because it's adiabatic. All right, so Q is just going to be equal to Q for the second step and going from 2 to 3. Now, in going from step 2 to 3, right, we're told that we have cooling at constant pressure. Okay, so we've looked at this a couple times before, so I won't rederive everything for you. But remember, for a constant pressure, for our constant pressure process, our first law of balance reduces to Q is equal to delta H. All right, where delta H, all right, is equal to delta U plus P delta V. Okay, so we have that then Q is equal to Q from 2 to 3, and that'll just be equal to H3 minus H2, okay, where that'll be equal to Cp times T3 minus T2. Okay, so just to write it down again, just to summarize, right, I have that Q is just Cp T3 minus T2. Then W, okay, so W would be equal to W going from 1 to 2 plus W and going from 2 to 3. Okay, so let's take this in steps. Okay, so in the first step, we had adiabatic compression. So Q is equal to 0. Okay, so if I look at the first step, okay, so I'm going from 1 to 2. All right, my first law of balance reduces to delta U is equal to Q plus W, where Q is 0. So therefore, delta U is equal to W. Okay, and then going from step 1 to step 2, right, I get that CV T2 minus T1, right, is equal to W. Okay, and so this is W going from 1 to 2. Cool. Let's think now in terms of going from 2 to 3. Okay, and going from 2 to 3, this is where I have cooling under constant pressure. Okay, so we had Q is equal to delta H, right, where my work term is just my P delta V. Okay, so in cooling from 2 to 3, right, work, right, again is integral of negative P dV, where here P is constant, right, so this could be negative P V3 minus V2. Okay, so then in summary, W would be CV times T2 minus T1 minus P V3 minus V2. All right, where we have everything in SI units now, in MATLAB, so if I want to calculate Q, so Q is going to be in joules per mole. Q would be CV times T3 minus T2. And W would be equal to CV times T2 minus T1. Actually, hold on, I gotta, did I get this right? Oh, CP, right? So I typed it in CP, right? I was thinking constant pressure. So typo. So this is CP as we had it written. So W, though, is CV T2 minus T1 minus P. Now, I should say, which P do I use here? Well, remember, P2 is equal to P3. So let me just mark this as being P2 so we know which value to plug in there. Remember, P2 is equal to P3. So minus P2 times V3 minus V2. So I get Q, right, and I would get W. Okay, so this would be Q and W for my process. All right. So I've got TP and V's throughout. I have Q and W for the process. If I were to sketch this on a PV phase diagram, okay, right, the key would be, and actually, right, the basic key is going to be, if I think of the first step on a PV phase diagram, okay, well, if I think of the second step, so if I have pressure versus volume, I'm going to have an isobar, right? I'm cooling at constant pressure. So I'm going to have an isobar in which I jump from one isotherm to next. Right? So I'm going to have an isobar in which I jump from one isotherm to the next at that P. Okay, cool. So that'll be a horizontal line. And then in terms of the adiabatic compression part, right, on a PV phase diagram, that's not going to be linear. Okay, why? Okay, so if I guess ideally I could take this and I could get rid of temperature in favor of pressures as well, but it's going to be a nonlinear change between that initial and final state. All right. If I wanted to, I could do the same exercise where T2 is, so I could have T1 is equal to VP over R, and T1 is equal to VP over R, and so I could get this in terms of relate pressure to volume, but the key would be that relationship is going to be nonlinear. All right, and so my initial state, I'd have some nonlinear path on my PV phase diagram, and then I'd have a horizontal isobar for the second step. Okay, and going from 1 to 2, all right, so if I look at P2, all right, since we have everything calculated, P2 is so that'd be 55.655 bars. Okay, so pressure's increasing, and then if I look at V1 and V2, all right, V1's 0.028, V2's 0.011. All right, so it's going to be this nonlinear path in which pressure increases but volume decreases. So nonlinear path in which pressure increases but volume decreases, and then I would have a horizontal path in which I jump from one isotherm to the next for that cooling at constant pressure. Okay. All right, so that was a fun problem. And then the last problem is, can we assume that we have an ideal gas? I think it's reasonable, and so I have open, must be here. Thought I had open. Let me open it up. Our appendix from Smith, Abbott, and Van Ness, only because it can look at the Lee-Kessler tables, all right, and see where exactly we fall. Okay, so if I find oxygen, okay, oxygen is here. Oh no, yeah. So TC, PC. So it's omega, TC, and PC. So oxygen has an omega really close to 0. Okay, so omega is 0.0222. TC is 154.6. Okay, and that's Kelvin. And PC is going to be equal to 50.43 bars. Okay. And so what I want to calculate here is I just want to show you the relative values, or reduced values. So TC is 154.6. PC, right, I mean, it's just a matter of, it's hard to make a judgment call here. Okay, and that's in bars. So let's do T1R would be T1 divided by TC. T2R would be T2 divided by TC. T3R would be T3 divided by TC. And we could do the same thing with pressure. P1R would be P1 over PC. P2R would be P2 divided by PC. And P3R would be P3 divided by PC. So if I look at my reduced pressures, so what I need to do is I need to take my pressure, and since my other pressure I had in SI units, it was in bars, so let me multiply by 1e to the 5. Okay, so now let's be more realistic, right? So I have reduced pressures are all, in my initial state it's 0.02, and then it's 1.1. Okay, but still pretty small. And reduced temperatures go from 1.9, 5, 1.8. And so if I were to look in my Lee-Kessler tables for Z naught, okay, and where am I? So let's just say I had a reduced temperature of 1.9 and a reduced pressure of 0.01. Right, you can see if I'm at like 1.9 and reduced pressure of 0.01, right, Z naught is really close to 1. All right, so the value of Z I'm going to get from the Lee-Kessler table is going to be really close to 1, really close to assuming an ideal gas. And I mean, I could do the same thing for the other states. T2, I'm at, say, 4.7 and a reduced pressure of 1.1. Okay, so now I'm at a reduced pressure of 1.1. Come on. So we'll say 1.1 and 1.2. Am I on the right table? And a reduced temperature of, 4 though, right? 4.677, right? So, here's 4 and 1 and 2, right? And you were 1.01, right? So it's pretty close. Okay, so it's, not anything significant. So, just, looking at some numbers, it seems like, ideal gas should be reasonable for the problem. Okay. Hope that helps. If you have any questions, let me know. So I didn't quantitatively sketch a PV phase diagram, but, you could draw your PV phase diagram as your characteristic dome. All right, and so, again, the initial state is, so I'm going to be in that superheated vapor region or supercritical part the entire time. First part would be this nonlinear path in which pressure is increasing. Pressure is increasing, and volume's decreasing. So I guess it would be pressure is increasing, and then volume's decreasing. So, and then we have a horizontal line for the second path. Okay. Hope that helps. If you have any questions, let me know.